So let's now think about a single layer neural network, and we're going to first consider its forward propagation details. So what do I mean by forward propagation? Well, I mean that we apply an input vector to the inputs of the network, and then we calculate the output. And that's all we're going to do in this particular little lecture snippet. And you can either use this sort of approach for generating output for regression, or you might want to then look at the output value and decide which class it belongs to. I'm particularly using here an example with a linear network, so we're just summing up the inputs, we're weighting the inputs, adding them up and generating the output. So let's move on to some more information about what we're going to do now. First of all, then, let's consider the case when we've actually got two inputs to a network. And what we're going to do is we're going to apply the input data set, which is going to represent the data we have available in terms of vectors. So xi is going to represent a single vector out of n from a data pattern data set. And it's going to be basically a vector which is, in this case, two-dimensional. And the overall data set X is going to constitute a series of these vectors. So each vector is two-dimensional. As I said, there's the x1 and the two elements of it. So the dimensions of the vector are along different rows. And in actual fact, we're going to have columns of these vectors which represent the different samples going into the network. So this is kind of the structure that we can have of a simple two-input network. And what we see, we've got an input vector x, which comes into the, in this case, just the single vector x, which is going to come into the input here. We're going to have a weight vector in this case, because we've just got a single output, so it'll be a vector. And what we do is we then generate the output by, if you like, doing a weighted sum of the inputs. So it's going to be x1 times w1 plus x2 plus w2 and plus a bias term, because to be general we need to add on a constant value in order to get this thing to perform useful functions. And that's of course writing it completely in this form. It's writing it in sum notation rather than vector notation. We'll come to vector notation in a second. And this is just listing all the variables so you can check what they mean later on. So we can of course look at this sum, right? So we're basically, in this case, we've got a sum across two, because it's two inputs. We're writing input element dimension now as being basically a j, so either 1 or 2 for the two dimensional case. And we're just summing up the weighted values of the inputs, w, j times x, j, and we're adding on the bias at the end. We can easily write that in matrix form as wx plus bias. In this particular case, let's just expand it out just so we're very familiar with all the terms. So the w is going to be a row vector, and the x is going to be, this is just a single data point, it's going to be a two-dimensional column vector. So this is what the equation looks like, wx plus bias, if we write it expanded in vector form. And we see that we've got this bias term, so the wx can capture a lot of what we're doing, and if we had high dimensionality x, it will do lots of calculations and lots of sums, but we've still got this rather irritating bias term. So just like we did with linear regression, we can say, well, let's think about putting the bias into the weight vector, and then we'll do something to the data vector as well, so the calculation all still works. So what we have to do is actually quite simple. We just append the bias again to the weight vector. So we just put it on basically in the last column. And in order to make sure the calculation does what we want it to do, that's easy. All we have to do is append the x data vector with a 1 in the last position. So basically the bias term gets multiplied by 1 and added on to the products of all the elements, and they all get summed together. Right, so we end up with this simple form for this two-dimensional case. What we've done now is we've effectively set another input, if you like, to 1 all the time, and then we can just represent the output of the network, which is a linear network, as just being w hat x hat. Nice and simple. So the nice thing about that is we've got a simple expression, and we have no other terms to worry about. So when we start doing analysis, it just makes it easier and more elegant, and it also makes it easier and more elegant when we're actually implementing it in MATLAB. So in this case, we call it net. That's the output of the network, is given by our w hat x hat. And in this particular case, let's just very carefully go through and look at the dimensionality, because it's always good when you're programming these things up to make sure you get it the right way round in MATLAB. MATLAB will complain. It will say the dimensions don't match up if you don't get it the right way around. We see here this is a 1 by 3 matrix. We see this is a 3 by 1 matrix, right? So 3 rows by 1 column, always rows by columns. And this is obviously going to be a 1 by 1. And again, you can always do the check that the internal dimensions, which basically butt up against each other when you're doing matrix multiplication, have got to be the same, otherwise you can't do the multiplication. And the outer ones of the expression could be a very long expression with lots of matrices in there. It's the end ones which will give you the final dimensionality of the output. So we end up with a 1 by 1, so a single value, right? And that's just the general rule, basically. A matrix of size A by times B multiplied by another one, B by C, you end up with one of size A by C. Okay. So how can we classify outputs using a linear network like this? Well, what we could do is we could say, well, if we've got the input data and we've got the labels for the output, and that's what we need normally to train the system, we could say, well, we're going to use certain targets when we train the system, and it could be use +1 for class 1 and -1 for class 2, whatever. Or another thing we could do is we could use +1 for one class and 0 for another. And then what we've got to do is, when we're actually running this, imagine we've trained it and we're running it, we calculate w hat, I hat for a particular data vector, and we have to decide then on the value of net, the value that we get out, what class it is. So what we have to do is look at basically the value and compare it with a threshold and say if it's bigger than a certain threshold, it's one class, otherwise it's the other class. And obviously this is a binary condition we're looking into. And typically a sensible thing might be halfway through, right? Halfway between the two. If thinking back though, if you remember the discussion of receiver operating characteristics, again it depends. What do we care about? Do we want to make sure that we never miss something we should be getting, or do we care about never making a mistake? So, the actual threshold is different than the actual fundamental underlying detector performance, and we can always, have a compromise between hits and false alarms by changing the threshold. But putting it 50-50, halfway between what we get for class 0 and for class 1 is certainly a good first step, or sensible, easy to justify thing to do to start with. Let's now think about what happens if we've got two outputs on our linear network. What's this going to change? Well, actually not much, except the size of the vectors. Okay, in fact, it's going to change the size of the weight matrix, because effectively we've got two outputs. So now we've got net equals w hat x hat. The x data, right, this is a single value again, is going to be the same, right? It's going to be, in this case, it's just one vector we're giving it, which is 2 dimensions of data, and we've appended it with a 1. Then what we find is now we've got actually got two rows in our weight matrix. So we've got one row, the first row, W11, W12, W13, corresponds to the output of one of the nodes, and the other row will correspond to the output of the second node. And in this case, we see that the dimensionality has gone up from 1 by 3 to 2 by 3 of this matrix. The data is still 3 by 1, but this basically means we end up with a 2 by 1 output, right? So we end up with 2 values coming out, and that's what we wanted. And that's what we said before. So we can easily extend this. In this case, we've got a 1-layer 2 output network, and now we're going to process n data patterns at the same time. Right, so we were just processing one data vector at a time, and our x hat was just a single vector, right? It was just a single column vector. But now we've got a series of column vectors, one for each data sample. So this is one data sample, this is the next one, all the way up to n. So we've got n data samples. And what does this change? Well, we don't have to change the weight matrix because the weight matrix stays the same. And again, this is a 2 output system. So we've got a 2 by, in this case, 3, because we've got 2-dimensional data plus this bias term here. And what it changes then is it changes the dimensionality of the output, right? So again, now we're generating an output for every, an output vector, if you like, for every input vector, right? So we've got n, if you like, input vectors, which we've now put into this matrix, and we end up with n output vectors. So just again, looking at the dimensions again, to start with, when you're doing these things, it's very good to check these things. We see this is rows by columns, so it's 1, 2 rows by 1, 2, 3 columns. This is now rows by columns is 1, 2, 3 rows, right? By 1, 2, blah blah blah, all the way to n columns. So this is 3 by n, and the output's going to be, in fact, looking at this here, you can see 2 by 3 times 3 by n, 2 by n. It's going to be a 2 by n. So we've got two-dimensional output, and we've got n values of them for each corresponding input vector. What we can also do now is we can stick on a sigmoid, and the reason we're going to do this, there's not such a big point in doing this for a single layer network, but when we start looking at multi-layer networks, we need nonlinearity in there, and the sigmoid is a classical nonlinearity. So in this case, what we're going to say is we get the output for a particular linear node, which is going to be called the net value, and then we're going to basically pass that through a nonlinear function, which is a sigmoid function. And for this particular function, the output of this function is 1 divided by 1 plus e to the minus input, which is going to be the net. So we can substitute net in as w hat x hat, so we end up with the output. Each output is going to correspond to this particular value. This is actually only true if we have a one-dimensional output for this. This has just got to generate one output for this actually to work. So for a single input vector, we actually have to do the output of this sum through a sigmoid function, and the output of this sum through the output of through a sigmoid function, in order to get a two-dimensional output, right? So each output basically is separately sigmoided. So in this case, if this is net 1 coming in to the sigmoid for this particular output here, basically what we do is we take the value which was net 1 and we put it into this equation, because we're using this function. So the first term becomes 1 divided by 1 plus e to the minus net 1, and the second one is 1 divided by 1 plus e to the minus net 2. Where in this case, like I said, we've got this two-dimensional linear output here for a single input vector, giving us a single output vector of 2 dimensions, and then each of these net values passes on an element by element basis into a sigmoid function, and then consequently we just have to transform net 1 in the top location on this vector and net 2 in the lower one on this vector.